it goes back to what we talked in the past, and that when we have an acid, we always make a conjugated base. So the conjugate base is what we're looking for. If the conjugate base is more stable, if the conjugate base is more stable, then the acid is stronger, which means that it's going to have an easier time to lose that H. So between these two H's, we're going to decide if we lose the H here, so we make a carboxylate. So the carboxylate has what we call a resonance structure. So we have a resonance structure here. And if we lose the H here, we have some inductive effect because chlorine is very electronegative. So we call this inductive effect. Inductive effect. So it means that chlorine is going to help us to make this negative charge on oxygen a little bit easier. So carries the negative charge away from the oxygen, and it helps the oxygen to be more stable. So we're going to compare the inductive effect to resonance effect. Let's do one at a time. One of these at a time. So let's start with electronegativity. We know if we look at the periodic table, going from the carbon to fluorine, electronegativity goes higher. So it goes like this. Going from iodide to fluorine, the electronegativity goes higher this way. So just a rough idea, we don't need to have the number. We don't have to have the number, we just rough idea. So let's say we have a nitrogen and we have an oxygen. So I try to use color and show the difference in different bases that we make. So if I remove the red hydrogen from nitrogen, so I make the conjugated base here. So this is my conjugated base. So I separate them from each other. Now if I take this hydrogen or proton away, I was calling hydrogen, but it should be protons. So if I take this proton away, then this is my conjugated base here. So we have two conjugated bases. One conjugate base is oxygen, negative. One conjugate base, nitrogen, negative. Now we know that oxygen here, remember oxygen is more electronegative than nitrogen. So if I compare O minus to N minus, O minus is going to have easier time to carry the negative charge. Hence, the proton or hydrogen attached to the O would have a little bit easier time to leave. So it makes this proton, the blue one, a little bit stronger than the red one, because the conjugate base that it makes is more stable. And we contribute that to the electronegativity of oxygen versus nitrogen. Of course, there are more things we can do as a practice. 13, A to D. We have the apply skill, 314, and we have many problems at the end of the chapter. 46, 47, 51, 60, and 65 to compare and use electronegativity as help for the acidity. What if we have resonance now? So in the resonance skill, let's say we have a molecule that made of nitrogen, attach a hydrogen to it, or proton. You have a nitrogen here also has a proton. Now the one on the right side, the blue one I call it, has a resonance structure. So if I remove this proton with a base to make a negative charge on the nitrogen, so this negative charge is next to a electron is next to the pi bond. And that's one of the resonance structure. Remember, we can move electron over here Move these two electrons. Oh, I forgot to draw the arrow. Move these electrons to the oxygen. So oxygen now would be negative and nitrogen would be positive. So we have a resonance structure that make it stable. On the other part of the molecule, this nitrogen, if it loses that proton to make the N negative as a conjugate base, there is no resonance structure for this. There is no resonance structure for it. So that, by definition, now we're going to say the one with resonance structure is a little bit more stable as a conjugate base. Hence, the acid this conjugate base comes from, this acid. And the proton attached to that acid, to the nitrogen, is a little bit more acidic than the one attached to this nitrogen. But the fact that the conjugate base here has a resonance structure, conjugate base here does not have a resonance structure. We have more practice to do, 15. Apply is 16. And the end of the chapter we have 46, 47, and 51. The next factor, this is factor 2. Factor 3 is, make sure it's reading, you can read it. So factor 3 is induction. So induction is really coming from moving electron away from the conjugate base. So if I have a molecule like this that has 2 chlorine, and these 2 chlorine are attached to next to the carboxylic acid. Then we have a carboxylic acid on this side. Again, we have 2 protons to compare. Let's remove this one first. So if I remove this one first, the conjugate base that I make, the conjugate base I have is O minus. And of course, this has a resonance structure, but at this point, we're looking at induction because both of them have the same resonance structure. So the chlorine, these 2 chlorine help remove the negative charge from the oxygen, make it more stable. Now, on the other part of the molecules, if you look at the carboxylic acid with the H, and you make the conjugate base from it, so if I make the conjugate base from this acid, there is no chlorine close by. There's a chlorine, not one next carbon, but a carbon away from it. Doesn't help us much, but so we don't have those 2 chlorine to help with the O minus. So if I go back and look at these 2 H's, so one on the right side, which I believe is a blue, is going to be a better one as acidity goes because it, by removing it, you make a better conjugate base. Then we have practice. We have practice 18, 19. We can apply the skill 20, and we have more at the end of the chapter 47, 59, and 51. So let's go look at factor 4. So in factor 4, we're looking at orbitals. So here we have a structure. So at one end of the structure, we have an alkene. So this is the alkene. Remember, alkene is sp2. On the left side, we have alkane, which is sp3. Again, two protons we can remove. On the right side, we can remove this. So that would be attached to a sp2. This would be removed and attached to sp3. We learned that sp, hydrogen attached to sp, is more acidic than sp2, more acidic than sp3. So we can tell by just looking at this structure that this hydrogen attached to sp2 would be a better acid. Now there is a 21. I'd like to spend a little bit more time on 22 because we have now a benzene group. So that benzene group has attached to an alkyne, and this alkyne, if you remember, we usually don't show that there's a hydrogen here, right? So this hydrogen is very acidic. The hydrogen is very acidic, and this hydrogen is not very acidic because this is sp2 and this is a sp hydrogen. So sp hydrogen is a lot more acidic than sp2. Let's say we remove that by what we call a butyl lithium, which is a base. I'd like to draw that. So we have 4 carbons attached to the lithium. The bond between the carbon and lithium is very polar. We can look at it as ionic almost. So I can put the negative charge on this carbon. So this carbon has 2 hydrogen and extra electrons, so that's why I make it negative, and it makes it a base. So we have a base here, and we have an acid here. And in organic, end of organic 1 and organic 2, we learn this is a very critical part of the synthesis we're going to learn. So if I use the base to react with the acid to remove the H, an electron from the H goes to the carbon. So the carbon, as I drawn here, would be negative. So we're going to learn later on this carbon negative, we're going to call a nucleophile, and it's very, very useful reagent we use in organic chemistry. There are more factors and more problems we can use. More problems we can use. 46 is one of them, and 61 is the other one. So now if you put all of them together, I really like this. I really like this crazy structure. So this crazy structure is really one of the strongest acids that organic chemists were able to make. As you can see, the structure, the acidity comes from this OH. So this proton here is the acid part. The H is really the acid part. Why it's so strong is because the CF3. So CF3 is electron withdrawing group. So we have a huge inductive effect. So we have an inductive effect for that H. We also have a beautiful resonance structure. Imagine if you remove that H, you have an O minus. So this O minus can have a big resonance structure. We can put the electrons over here to make a double bond. This double bond moves over here, and this unit and resonance structure repeat itself on both sides. Repeats itself on both sides. Then we can have now nitrogen. Oh, I forgot the double bond here. So nitrogen now is going to have the double bond to the sulfur. You can have a nitrogen double bond sulfur. The sulfur now is attached to a single nitrogen, and double bond here is O minus, and they got an inductive effect here. So that resonance structure can repeat on this side, so makes that conjugated base